the title of the talk is Practical Rowhammer Attacks and Defense. So I think the keyword is, I've given a lot of talks over the years about Rowhammer, and the keyword here is really practical. And I will try to basically convince you that the attacks are quite real, right? And also, I think some of the mitigation really, some of them are already being deployed, and I think we need to deploy more essentially to stop this class of attacks. But before I start, maybe a show of hands, right? So that I know basically how much you know, so that I know how much I should explain, how much background I provide. So if you've read a news article about what, okay, that is one. So maybe this talk is going to be shorter than the next one. Okay. So what if you've read 10 news articles about one? Okay, somebody really interested. Good. Okay. So yeah, so maybe the next one. So it's in the news, right? At least 10 times. So do you think that Rowhammer is fixed by now? So skeptical. All right. Okay. Yeah. So good. So it's gonna maybe make my next statement not so provocative. That DRAM is actually more broken than 10 years ago. So the issue, as we discussed soon, was discovered for the first time or became publicly known about 10 years ago, more than 10 years ago. Yeah, so we had 3 years of trying to fix it, right? And I would show you during this talk that actually, in fact, despite all this effort that people have put both in industry and academia, right, DRAM is today more broken than it was 10 years ago. Okay? Right. So what is Rowhammer? Maybe just a very brief introduction. So this is a problem of electrical element scaling, right? So transistor and capacitor scaling. Right? So we have this Moore's law that is now kind of giving out, but still, you still hear that we're still making them a little bit smaller, right? And because of that, back then, let's say like maybe 10, 15 years ago, maybe 20 years ago, DRAM is a capacitor-based technology. If you want to store a piece of information, you will store some charge, and the high charge, you encode it to a value of 1, for example, and then you can store data. So one capacitor, 1 bit of information, pretty much. And then you have transistors that sort of allow you to access this information, given a specific address inside here. So you could imagine on the left side, 20, 25 years ago, features were big, right? So we would have big capacitors, so to store one bit of information, we could store a lot of charge. And now years later, you could imagine that transistors and capacitors have become much smaller, right? And it is nice because it means that in the same area you could pack more of these capacitors and more of these transistors. And as a result, the amount of charge that you need to store in each of them has become smaller, right? And also they become very, very close to each other. And then people realize that, okay, because they're so close to each other, what they do is that you activate one row of this, you access DRAM in the granularity of the row. You could access one row very quickly. So before I explain that, so as I said, DRAM is a capacitor-based technology, right? So, and if you remember your courses from high school, what do capacitors do? They leak charge over time, right? So, and to make sure that your data doesn't get corrupted because you store data by charge, every now and then you have to go to DRAM and say, please refresh, so recharge these capacitors that you have, right? And this happens, in commodity DRAM technology, up to 10, 20 times a second. So 10, 20 times a second, every bit of information that you have in your device gets refreshed, right? So this happens regularly. But what people have discovered is that between this, 2 times when a piece of data is refreshed, if you access one row of DRAM very, very quickly, right, some charges start to leak from adjacent rows. And if you do this fast enough before DRAM has a chance to refresh one of the rows, then enough charge leaks from one of these capacitors from one row to the other that the system can no longer recognize that it was actually a high charge that was stored there. So, for more software-oriented people like myself 7, 8 years ago, this would mean that you would access some part of some location in memory,
and suddenly you get bit corruption somewhere else in your memory. So this is how the manifestation of it from software. Right? So yeah, so this was this was disclosed, discovered, presented by Onur Mutlu's group back then in Carnegie Mellon in 2014 by some chance of the world. He happens to be in the same department that I am now. So he's not also at ETH, but back then he was at Carnegie Mellon. So his group disclosed this, right? And then they showed on an FPGA it affects about 87% of all DDR3 memory that they tested. So quite a large fraction. So we also did our own study. Took us quite a bit to publish, right? And then basically our study showed that, in fact, if you do it from a real memory controller, right, on an Intel system, it actually, the number is lower, it's about 42% or so. So this was around 2015 that it became sort of like more known in the security community. There was a researcher at Google that built the first exploit. And then from then on, it came in the radar of people who cared about security, right? And I was finishing my PhD, trying to maybe do a postdoc, right? And this sounded quite interesting, right? So the question I was asking, right? So because this is hard, right? It sounded like a good puzzle, right? I was thinking, how useful are these bit flips? Can we actually, so they seem to be random, right? Beforehand, because it depends quite a bit on the manufacturing technology. So it is device dependent. So you don't know where you get these bit flips. And it's only a single bit corruption, right? So the question, and then people would think that, okay, maybe maybe in some cases you can build exploits out of this, but it's mostly probably a reliability problem. Maybe you shouldn't worry so much about it, right? So the question that we were kind of fascinated by was actually how useful are these bit flips, and can you actually build a real attack using these bit flips? And this is sort of like a question that took us 4 or 5 years to actually try to answer. And so the answer is that pretty much in any environment, if the attacker could control how data is stored in memory, you could build a reliable real-world attack. And I'm going to show you some examples of that, right? So the first one is Rowhammer attacks on page tables, which is an instantiation of also the first attack that was done by this researcher at Google. So for maybe those of you who maybe need a little bit of help remembering some topics in operating system, if you know that every sort of nowadays almost every modern system that you use, such as a laptop and a mobile phone and whatnot, you essentially have an MMU, so you use virtualization to virtualize your memory. So all the memory accesses that go through your system are essentially through virtual addresses. They are virtual addresses. They're virtualized. So which would mean that you have a memory management unit in your CPU that does this translation from virtual addresses to physical addresses. Okay. And this translation is done by this data structure that is known as page tables, right? So the MMU looks at page tables to translate a virtual address to a physical address. So on x86, there is a register, in this case CR3, different architectures, different registers that point to the root of this page table tree. So, and then your CPU essentially walks this page table tree to translate this virtual address to this physical address. So your MMU goes to this page table, the first level of the page table, and then uses some bits of this virtual address to figure out which location inside the page table you should go to. And it finds a physical address that points to the next level of the page table. Then, you go to this page, this physical page, right? And then you use the other bits, right, to figure out, okay, which entry now should I read? And now this entry essentially tells you, okay, your actual physical address is in this location. Now, of course, this is not exactly how it works. I try to simplify it a bit so that it would be easy to explain. But this is the concept is pretty much the same. So this is how page tables work. And now why am I telling you about page tables and MMUs and these kind of things? It's because these are like really nice targets for Rowhammer attacks, right? So if you think of Rowhammer, imagine that you have this one physical address bit in a page table page, right? If you flip that one bit, right, then it would mean that your virtual address, now your virtual page will point to a different physical page, right? Okay. And now if this other physical page also happens to be a page table page, right, that would be really nice. So I have a question for you. What happens when we can, as an attacker, we can directly write to page table pages? So what happens? I'm not going to answer that. I'm going to wait till one of you answer. Can cancel the lecture. Okay. So no takers. So if no takers, I will answer it myself. So it basically means that you could essentially write physical pages in your page table, right? So through the virtual address that you have, you could just essentially write any physical address that you want, right? And then you could essentially read all of physical memory or write to anywhere in physical memory, right? This is not good, right? So you don't want to be able to do that. Yes.
Can you precisely control that? I mean,
that's a very, very good question that I'm not going to answer in this lecture. And this is exactly basically what we did, trying to essentially figure out how. So there is this low-level memory allocator in Android and Linux-based, many also Unix-based operating systems that are called the body allocation, right? And this body allocator has a predictable behavior. And we essentially, Victor, one of the PhD students at the time, essentially looked at how you could exploit the predictable behavior of the body allocator to make sure that a page table page lands exactly in a location that you want in physical memory. So first, we go through memory, look for locations where you have bit flips, then we release this page back to the system. Then since we know how body behaves, because it's a deterministic allocator, essentially, then we know, okay, how should we allocate page table pages so that this page table would land exactly on that location that we want. So, and this we could do in a deterministic way.
Excuse me, can you see the output of the page table? I mean, you want to, for example, see whether this virtual address points to a particular physical address. Can you see the output of this?
So when you read it back,
yeah, for example, you want to with particular virtual address, you want to point to a particular physical address.
Right.
Can you see that the output of the page table is exactly the physical address that you want? No, it's not visible.
So typically, we don't directly leak the page table entry, right? So we don't leak that, but we could see that, okay, that it is flipped, because now instead of pointing to a data page where we do if we be working correctly, we would be essentially dereferencing a normal data page. But after the bit flip, we see that when we dereference it, we actually read page table entries. So then we know that the attack has been successful. Right. Okay. So I'm going to show you a demo, right, of this attack in practice. So we actually built this exploit, right? And on the left side, you can see like the screen of the phone. On the right side, you can see, a shell. So this is a non-privileged shell. You could imagine any app having this type of access, right? So he's now running the exploit. And so finding these bit flips, depends on how vulnerable your DRAM device is. It could take you from, a couple of seconds in this case to maybe even a couple of minutes. So he already found a bit flip. He already, landed the page table. So all of this happens very, very quickly, of course, right? And now he's essentially scanning the memory. He's writing page table entry, trying to find the credential structure of this process, because he wants to write zeros to it so that he would then have root. So, and of course, he makes a lot of other processes root, right, but not the one that he controls. But finally, he finds the correct one, and he gets root, right? So here now we have an app that doesn't have any permissions, right? And essentially, we are using Rowhammer to get root on this phone. So now the rest of this is, of course, just showing, the model number, that this is updated and everything and so on. So this was an attack that we did in 2016. But all of this still applies with variation. In fact, I just had a student who reproduced something like this with DDR with a recent DRAM device on a most recent system. So this still works with minor variations. And typically, whenever vendors want to fix this, they disable some features that we use to make the exploit possible. So in this case, there was ION that would allow us access to uncached memory, which would let us get bit flips fast, right? So they disabled that, made that a bit harder, but you could do some minor variations and it would still work, right? Yes.
I would imagine that writing some zeros to some random memory would somehow make a crash.
Yeah. So the way. So indeed, you have to be careful that when you're actually doing the attack, you do not corrupt other data that you have on the system. But what you could do is that, so the system oftentimes allows you to allocate contiguous memory. Or you could allocate memory and later do a side channel attack to figure out whether the memory that you allocated is contiguous or not. And once you have contiguous memory, you sort of know that, okay, if I sort of do the hammering, right, I can maybe avoid the edges to make sure that I don't corrupt basically data that is on the sides. But in our experience, this happens very, very rarely. So even if you're not careful, let's say in 90% of the cases, this works quite well already. Okay, so this was one example natively. Let me also look at my time to make sure that goes of course slower than I expect. So I try to go a little bit faster and maybe skip the next demo. So this is now the next one that we built was a remote attack, right? So the idea would be that I'm an attacker and I go to Google and I say, I have this very great ad for people who may be working in the Bochum area, who might be interested in security, right? And I want them to see this ad, right? And then the idea would be that, if I pay Google enough, then Google is going to show my JavaScript code to you, right? And then the question is that, can we use Rowhammer in that JavaScript to compromise your phone? So that's sort of like the target. The idea here is that, for those of you who have written JavaScript code in the past, so JavaScript is like sometimes it's very lax, right? So it has these arrays, right, that you could allocate like this, and then you could store pretty much anything that you want in them. You could store integers, you could store like strings, doubles, whatever you want, right? So there's no other programming language that I know allows you to do this, but JavaScript does. And the question is that, okay, so how does the JavaScript engine, does this in the background, right? And this is done, so here in memory, so, you would have your string, double, your int, double string, whatever. And then, the technique that it uses to actually support these different types inside the same container is known as nan-boxing. And the way it works is typically, instead of just storing the data, it would use a tag that would let you distinguish between objects of different type. Okay. So in this case, we have two different type of objects, right? One is a float and one is a pointer to a string. And in this case, we have, created them in a way that, the tag, the payload is the same, but the tag is exactly 1 bit different, right? So a pointer and a float, their tag is only 1 bit different. And all sort of alarms should go off in your head, right? Because only 1 bit is different, right? Which would mean that if you flip exactly that bit, you could change types. You could flip types to each other, right? This is exactly what we did. We call this type flipping with Rowhammer. So, we could essentially take any pointer, right? And then we could flip a bit into the tag of that pointer. And when we do that, this pointer suddenly becomes a double, right? That we could then read. And this primitives gives us a pointer leak, right? So remember that pointers, you're not supposed to read them in JavaScript, right? So there are these mitigations, right? Address space layout randomization that randomizes the location of these pointers in memory to make it difficult for software vulnerabilities to exploit the system. So typically you don't know pointers in JavaScript. But here with this primitive, you can essentially leak pointers. And the other thing that you could do is essentially take a float, right? And then flip a bit in the tag and make it a pointer, right? So you could take any float and you could make it a pointer. And essentially this provides you with a primitive to do an arbitrary craft, okay? So now the question is that I have for you is that what happens when you can craft counterfeit objects in the browser? Where you can take any pointer and make it so this is also quite bad, right? So essentially you can create an object if you do things right. And then this object, essentially, since you crafted it, you control all the headers and so on, you can say that this object is the biggest object in the browser and has access to the entire memory of the browser, right? And this is exactly what we did. So this gives you essentially arbitrary read writes in the browser. So this is what we did, Pietro. I'm not going to go into the details. The exploit is a little bit complex, right? So first you need to sort of like break ASLR by flipping a bit. And then once you do that, then you could craft a pointer, but it needs to be a very specific type of object. So because you don't know a lot about the internal information in the browser. So we looked for an object that you only need to know just the pointer, and this happened to be the string, the read-only string object. So now we have a primitive that gives us arbitrary read. And so we use this primitive to read the header of an array object, which gives us read-write. So, and then we use that information to craft a counterfeit array object, which also then gives us arbitrary read-write. Now, I don't go through the details of it. If you want, please read this paper. So this is how we were spending our Christmas holiday in 2017, because the reviewers really wanted this exploit.
Can you get back to the previous slide?
Yeah.
How do you change exactly that single bit? You know, you probably know where these payload is or tag are stored, but then you need to physically know exactly where the bit is to actually toggle the other one over. Read, write, and the neighbor one.
Yeah.
To flip this.
Okay, so let me try to provide. So of course, the details. So you know, a lot, but I try to just give enough. So typically, what we do is that we sort of like so JavaScript provides you to have a different view of. So we would allocate a large array, right? And then we could have different views of this array. For example, an int 32 view of this. And then these you can access very, very quickly. So we would write a lot of value in this array, and then we would hammer this, and then we will see that okay, one of these specific offsets you could essentially flip. And then once you know that okay, if I store a different object here, now if I could flip that bit, then I could get this type flipping primitive that I'm looking for.
You need to have some information about how Java actually.
Yeah, exactly. So, but this is an information that you could do beforehand, right? So this is you could look at this browser, see how it works, and once you can craft your exploit that way. Okay, so I have a demo, but I'm not going to go through it. We don't have time, unfortunately. But you can find it online. Just look for this paper and this on YouTube, and you will find this. So we maybe cross this one. Okay, so I hope by now I've convinced you that all it takes is just a few flips, right, to compromise systems in different scenarios. So we should try to fix this, right? So we care about security. We do all this type of security research, try to make software secure, try to come up with new environments that are trusted, right? So I think it's important to make sure that these low-level attacks do not stay. DRAM is problematic, right? So you cannot update it, you cannot patch it. You put it in a system, it stays with you for 5 years if you use your system for 5 years. So we should try to build mitigations for DRAM that sort of withstand this test of time, right? Right. Okay. So this was all DDR3, and then DDR4 came out around 2015, and then started becoming really popular around 17, 18, right? And people were saying, people like Samsung, which sells like half of the DRAM on the planet, were saying that we have built Rowhammer free DRAM, right? So, and then you should not worry about this anymore. You just let go of your DDR3 system, buy this DDR4 system, and it's all good, right? So you should trust us. We fixed this. You shouldn't worry about this, right? And it was not only Samsung, right? It was also Micron. So if you look at the data, this is a snippet from one of the data sheets of Micron. And then basically, if you read through the technical detail, it says that they do something in the background, TRR, which we will talk about, and then because they do that, it would mean that you can send as many activate. There is no restriction to the number of activate commands. So you could send a lot of these activate to any row that you want within the specification, and nothing should happen. So what is this? What is this TRR? Right? So this is the question we were asking ourselves, 2017 or so, right? It felt like they're now doing some sort of mitigation inside the DRAM device, and this is stopping these bit flips. Good. So, and so this TRR stands for target row refresh. And then, if you read, through the patents and so on, basically what you find out is what they're doing is essentially, you're activating some row. It basically essentially tries to detect that a certain row is being activated too often, right? And it would try to do a preemptive refresh for this row. So you do not wait for this standard refresh operation. So you detect that the row is being activated too often, and you would essentially refresh its victims. And this way, you would stop the attack. Or this is at least the theory that we had that how it would work. So the big question was, does it work? Right? So should we trust them, and should we be happy have DDR4 here all secure? Right? So we were like, okay, we are researchers, people say something, we always go and test whether, what they say is indeed what is happening. So what we did back in 2018 or so, or 19, we bought 40 recent DIMMs, so memory, from these 3 vendors, so Samsung, Micron, and Hynix. So they hold 90, it's a monopoly, DRAM is a monopoly. So there are these 3 companies that sell 95%. This is actually even more, 99% of DRAM on the planet, right? So we went and bought these DIMMs. We just went to our favorite web shop and just bought 40 of what we could buy, and then we tried some of these patterns, right? And essentially, there are 3 of them, right? And then the idea would be that you would access rows in this red part, and then you would see bit flips in these blue rows, right? And then this one is the most popular, was the most popular one back then. It's called the double-sided attack, where you would have one of the victims essentially sandwiched between these 2 attackers. And if you would hammer these 2 attackers in this double-sided fashion, the idea would be that because there are like more possibilities for charge to be leaked from this middle row, right, the chance that you would get a bit flip in this middle row would be higher than the other possible scenarios. Okay. So we took these 40 DIMMs and we tried these 3 different patterns that are known at the time, and this is what we found out. So on the y-axis we have the number of bit flips. On the x-axis we have the manufacturing date of the device. And so before, and we also had some DDR3 devices from the past, right? So for DDR3 devices, you could see that these patterns would trigger bit flips, right? But then for DDR4 devices, right, we could see that there are no longer bit flips. So, they seem to be doing something to stop these bit flips, right? And then the question was, okay, they did something, but how are they doing it, right? So how could they detect these access patterns and stop the bit flips? So this is the next question that we asked, right? Now, understanding how it works turned out to be more difficult than we hoped. And this is where we spent more than a year trying to reverse engineer what was actually happening. Okay, and the main reason for this is that typically, when we want to reverse engineer a component inside the CPU, we have, we have access to this timing information, right? So we would execute a piece of some instructions, right? And then we time how long it takes, and then we could use the timing to figure out, okay, the CPU is doing branch prediction that way, right? So this is sort of like we had that possibility, but here, DRAM is a synchronous protocol. So every command that you send to DRAM, you wait a certain number of cycles, and then the result should be ready, right? And because it's a synchronous protocol, it means that we cannot use timing to reverse engineer it, right? So which makes reverse engineering DRAM harder, right? So this we could not use DRAM because all the accesses would take the same amount of time, regardless of whether some TRR would happen in the background or not. So this was problematic. So what did we do? So we called up our colleagues, happened to be Professor Mutlu again, who had built an FPGA-based memory controller. And so essentially this FPGA-based, so it's a soft memory controller, right? So we could try to run the device. So the idea would be that, because then this is like, we don't have to basically respect the protocol, right? Specification. We could just do whatever we want, whenever we want it. So the idea was that we could send these commands to DRAM in whatever order we wanted, violating the timing as much as we liked, right, to understand exactly how they deploy this mitigation. So they didn't have DDR4 support, so we helped them, we talked, and we also convinced them that they should build DDR4 support because DDR4 is what we were looking into. So we built support for DDR4, and then we ran a lot of reverse engineering experiments. So there were like a lot of these meetings that we had. We would look at the data, and then we would sort of try to design like the next experiment to understand whether our conclusions about the previous experiment is correct or not. I don't know. Some of you may have done reverse engineering. It's not really an exact science, right? So you sort of like a little bit of like alchemy, right? You try something here, you get a feeling of how it works, you go to do a little bit things more there. And then after, doing this enough, you start developing an understanding of how the device that you're reverse engineering is actually working. So we did that for quite some time. And now I'm going to try to, present a cleaner version of basically what we found out. So we built, by the way, 2 different reverse engineering techniques. So the first one became trespass, and then we built another one that became UTRR. So one of them provides us with a coarse way of looking at how TRR works, right, which I'm going to talk about mostly here. And the second one, it provides us with a more fine way of how TRR works. So it's a more fine-grained observational channel, a bit more advanced, right? If you're interested, you can read the paper. So I'm not going to talk about it today. I'm going to mostly talk about this one, which is also the first paper that we published. Good. So we sort of started building a theory by looking at the patterns that if there is a TRR solution, right, it needs to have a sampling mechanism, right? So whenever DRAM accesses are coming, there are a lot of them coming between every 2 refresh window, right? You could have like 1.3 million activations, right? So this is coming. And you have probably like your mitigation is probably looking at these activations and try to say that one looks like could be doing Rowhammer, right? So this is sort of like a sampling mechanism that you would have. And this should happen, as I will soon show, this should happen at memory access time. And then you need to have an inhibitor mechanism, right? So you need to, whenever you detect that, okay, maybe there is somebody doing Rowhammer, you need to have another mechanism to go and try to fix the victims of this row that is being attacked. We call that the inhibitor mechanism. And so this inhibitor mechanism works by doing extra refreshes, right? So preemptive refreshes before bits start flipping on these victim rows. So the main question that we wanted to answer was, when do these internal refreshes happen, right? So that was the first sort of question. So we designed this one experiment using this platform that I showed you. So on a Hynix team, so we disabled these refresh commands. So there was no refresh commands whatsoever. So this is, of course, outside of the specification now, right? So you're supposed to send, every 7.8 microsecond, you need to send one of these refresh commands to your DRAM device, right? So this is now running outside of the specification. So we wrote values to memory, right? And then we hammer for 64 milliseconds, right? 1, 2, a specific in a double-sided fashion, and then we check for bit flip. So a relatively simple experiment, right? Basically, we are doing hammering without refreshes enabled, right? And so you already here, we could see like some interesting results. So on the y-axis, you could see the total number of errors, and on the x-axis, the number of hammers that we did in our experiment per aggressor row. So, in the beginning, you would see like very few 5,000 accesses per aggressor, and then this would go up to 50,000, right? And then here, there are some interesting observations, right? So first of all, JDEC, if you look at the standard, it says that you should not, so if you write a piece of data to DRAM, you should have retention for 64 milliseconds. So data should not get corrupted in 64 milliseconds. So which would mean that these corruptions that we are seeing here are not retention failures, because this experiment runs in 64 milliseconds. Okay? So if they're not retention failures, what are they? They are Rowhammer failures, right? So these are Rowhammer flips. So this is the first, basically, essentially, thing that we learned with this reverse engineering, that TRR, whatever it is, happens at the refresh command, right? So the refresh commands that you receive is essentially doing TRR and fixing these rows in the back. The other interesting observation that we will soon get back to, like in a couple of minutes, is that DDR4 cells are much leakier than DDR3 cells, right? So here you can see, like after about 25,000 accesses per aggressor, you start seeing bit flips. So for DDR3, this was like 150, 200,000 accesses that you needed to do, right? And this is because, the features are becoming smaller, things are becoming less reliable, right? And this is a trend that we are going to see with DDR5, with DDR6, which means that this problem is getting worse, right? So, still opportunities to do more interesting research, right? For the next 5-10 years, perhaps. But I'm getting a little bit tired. We'll get to that soon. There's always it has become a little bit of a cat and mouse game. We will discuss that. Okay, so now the next question that we wanted to figure out was what is the size of the sampler? So you have this sampler, right? And we knew that probably this sampler does not store a counter for every row, right? Because that would be very, very expensive. So probably there is a limited size of some sort for this sampler. So we designed this experiment where we pick n aggressor rows, and this n we would play with. So we start from 1 and we go all the way to 20 or so. And then we would hammer them for around 10,000 activations. And then we send m refresh commands. So, and then the idea would be that we would like to see whether these refreshes that we send fix the potential Rowhammer bit flips that we would see for these aggressors that we have picked, for these addresses that we are hammering. Okay. And then we repeat this experiment for 10 times. And then the pattern that we would have is essentially in this order, right? So where there is like a kind of like a checkered patterns where we would have one victim, one aggressor, one victim, one aggressor, one victim, and so on. And here is the result of this experiment. So it's a kind of a complex plot. I will try my best to explain it. So this on the x-axis we have the aggressor rows. So this would be this parameter, right? And on the y-axis would be the number of refreshes that we would send per round. So there are a bunch of interesting things, and on each of the entries is the number of bit flips. So so if you see that, for example, here is 0, we are not seeing any bit flips here. But here, for example, we will see like 4,300 or so bit flips on this specific configuration, for example. Okay, so let's take a look at, let's make some observation, right? So the first one is that, so here we have one aggressors, right? And then we see that as soon as we send one refresh, right, we do not see any more bit flips. So these bit flips that are caused by these aggressors are essentially fixed. So when we go to 2 rows, so this is in the double-sided fashion now, right? We see that, okay, so first of all, we see in the, if we don't send any refreshes, there are a lot of bit flips, so a lot of Rowhammer bit flips, right? But as soon as we do one refresh, we send one refresh, we can see that the number drops rapidly, right? So which means that, this TRR knows that that row is going to be potentially subject to Rowhammer, so it will fix that one. And the next one that we send also fixes this one other one, right? So it's probably a bit flip that is happening maybe on the sides. That is less likely that the one in the middle, which is where a lot of charge could be potentially leaked. And then the same trend you see if you go to 3 aggressors, right? You will see that, okay, so as you send more refreshes, then more of these victims are potentially being fixed, right? But at some point you see that the number starts plateauing. So the more refreshes you send, it doesn't help that much anymore, right? And then here, so there are, so the main reason for this, we think, is because whenever the mitigation selects an aggressor to be for mitigation, it is essentially, there is probably a bit internally that says, okay, this is, I fixed this, it is discarded. And once it is discarded, it could be that one of the victims on the sides is essentially not mitigated. The idea would be that in the next round potentially we'll catch it again, and this is probably how the mitigation works. But how exactly is it implemented, I cannot tell you. But we see this trend again, right? So we see, so for example, here when you go to 4 aggressors, essentially at some point these refreshes that you send do not help catching the bit flips anymore. And then so this starts with increasing the number of aggressors and the number of refreshes until a point, and after some point this starts becoming sort of like not changing that much anymore. So, and we looked at this data and we assumed that, okay, so the best reasonable explanation for this is that you have a sampler that has, can keep track of 4 aggressors, right? And then once, you go above this threshold, it doesn't matter if you send more refreshes, the aggressors are already taken care of, and the rest you will see a lot of bit flips for those that it was not tracking. So based on this, we designed another experiment now. And this time we did native refresh. So this is a normal device that is being operated inside the specification now, right? And we increase the number of aggressors. And then we see that once we go to 5, we start seeing bit flips, which essentially, validates this theory that the sampler only has 4 entries, 4 counters for 4 rows. So this is like, when we saw this, we were like really happy, after like a year and a half of, reverse engineering, we could essentially get a bit flip on a device that was advertised to be Rowhammer free. Now our excitement died very quickly after that, because we were like, okay, they all should be working like this, right? So we tried a different DIM, and then we very quickly realized that it's using a completely different mitigation. So not working like the previous one at all. So this meant that, essentially the mitigation landscape is very fragmented. We even noticed that inside the same inside the same vendor, different generations do the mitigations differently, right? Which means that, and this reverse engineering takes a year maybe per device. Maybe once you get really good at it, you can do it in a couple of months, but this is not something that you want to do, right? So we thought that, okay, this is quite difficult. So what else can we do? The solution is automation. So we build a little fuzzer to essentially try to find out this. We randomize some parameters like the number of aggressors, the distance between the aggressors, and try to find out whether we could find bit flips on these different devices. So this became the trespass fuzzer. So every time we randomize the number of aggressors, we decide what should be the distance between these different aggressors. We hammer, we check for bit flips, happy. If not, we repeat again. And we do this for 6 hours. Okay. And we found, so on different devices, we found some interesting patterns. So one is this 4-sided, which is very similar to the one that I showed you about. I showed you 5-sided. But the idea would be that we hammer, like you would do double-sided, you would just like add one more row, right? And then this pattern also happened to be quite successful in some devices, Micron devices, which we call assisted double-sided, where you have this sidekick that essentially tries to confuse the mitigation, right? So you have like this one other row that you also use, and this other row essentially throws off the mitigation. Then you will see bit flips here in the middle. So we tried it on these 40 devices that we have from before. So here you can see, the dates are from 2016, manufacturing date, till 2019 or so. You can see that there are many different patterns that would work on a certain device. So sometimes up to even 129 patterns on a certain device. Yeah, and then you would, and then this, you would have, some of these would have a lot of aggressors, right? So which is kind of counterintuitive, right? Before you are trying to maximize the number of hammers that you're doing for a given aggressors. But now by increasing the number of aggressors, you're reducing the number of hammers that you're doing for an aggressor. But this is exactly what you need to do to bypass the mitigation. And this is only possible because these thresholds have been rapidly dropping, right? So this is sort of like, I would say, the surprising point of the results that we had in this work. So we found out bit flips from these 40 devices on 28%. And so the new Hynix DIMMs, they seem to be doing something different, so we couldn't trigger bit flips anymore, okay? So the question was, can we do better, right? So 28% still feels like better than DDR3, right? And then, so we started like really thinking more formally about this. And we realized that, okay, so what, and trying to understand really what TRR is doing. So you could think of it as, there are these activations that are going to these different rows. So it's going to this row A, row B, row C. And then there is this refresh that comes, right? And this refresh needs to decide that it's going to do TRR. Needs to decide which of these rows it needs to essentially protect, okay? And if you think about this, this is a known problem, right? This is frequent item count, right? So there is like essentially, and this took us a couple of years to find out that in this, we are trying to essentially, they're trying to solve frequent item count problem, right? You're trying to find an item that is repeated more frequently than others. And, it's sort of, there are a lot of algorithms out there, right? But this is a security application, and you need to do frequent item count precisely, right? The problem is that doing precise frequent item count is expensive, because you need to have a counter for every essentially row if you want to. You need fewer counters, if you do algorithms such as misery and whatnot. But still the number of counters that you would need is a lot, which would mean that this is an expensive sort of mitigation to implement in hardware. So probably what they're doing is they're estimating these frequent items, right? And the other problem is that this Rowhammer threshold, as I mentioned, they're dropping, right? So for DDR3, it's 150, they're going down to 225K, and it is still dropping, right? And then you have so many millions of activation to hide your accesses to these different aggressors, right? And so which would mean that because you need very few accesses, you have more possibilities to hide your aggressor from the mitigation, right? So which would mean that essentially the precise estimation of which ones are aggressors, it's becoming harder, right, with newer devices. So, and then the last observation is that the existing Rowhammer patterns, including trespass, like four-sided, here are again like the visualization of them. So, for example, double-sided and four-sided, they're essentially hammering aggressors in the same frequency, right? So, in the single-sided or double-sided, you're sort of taking two aggressors and you're like hammering them with the same frequency. If you do four-sided, similarly, you're hammering these rows with the same frequency, right? And if you think of an algorithm inside a device doing mitigation, right? These are the easy cases for frequent item count, right? Essentially, it tries to find out these specific aggressors that you're hammering the most. So yeah, so these patterns are hammering the aggressors uniformly, and these are the easy cases for the estimation of frequent items. But we are aggressors, we are attackers, right? We do not necessarily need to make the life of the mitigation easy, right? So we do not need to hammer our aggressors with the same frequency, right? So we could pick a bunch of aggressors and we could essentially hammer them with different frequencies. And this is essentially what we did. And this creates a new generation of Rowhammer access patterns, which we call non-uniform patterns. And they look like this. So we tried many different visualizations. Reviewers hated us, but they seem to like this one the most. So this is what we stuck with at the end in our paper. So this is one sample of one of these patterns. So here you have like a pattern that repeats, I think goes up to, I don't know, 200 something. And then, you have a base frequency, which is like this 96, right? And then this sort of like part of the pattern repeats every 96. And here you can see, for example, one row is being hammered for like half of this time. And this is repeated in every one of these base frequencies. And then you have another one, right, that is repeated less often, hammered less. You have one other row that is hammered very little, but is repeated more often. And so you can see like there are these different aggressors that are being hammered at different granularities at different times. The question is that how often should we hammer an aggressor? When should we hammer an aggressor? And how long should we hammer an aggressor? Okay. And so these concepts map quite nicely to concepts, signal processing concepts, right? So frequency, phase, and amplitude. So essentially what we did was we pick a bunch of aggressor pairs, and then we decide we randomize frequency, phase, and amplitude, right? And this is sort of a fuzzer that Patrick made last year. And essentially what he showed was that once you start doing that, so he would essentially randomize these patterns, then build the pattern, and then would hammer, right? You start seeing more bit flips. So this is essentially the fuzzer. So you take a bunch of aggressors. So before you would essentially, in the previous cases, you would sort of say these are the ones that are going to trigger bit flips, right? But now any one of these sort of aggressors could potentially bypass the mitigation. So we don't know a priori which one of these aggressors are going to bypass the mitigations, right? And then we essentially fuzz this, right? And this is the result, right? The results were much better than we expected. Actually, we could find bit flips on 40 newer devices that we had bought. So here I have sort of the different vendors. So Samsung, I think, Micron and Hynix. So we had trespass from before, right? And you can see that in many cases, it does not trigger bit flips, right? And then with Blacksmith, we could find, first of all, on all of them, but also in many cases, orders of magnitude more bit flips. And so this we open sourced, right? So, and this is, I know now, deployed by many companies. So, I mean, I know at least 2 of them that sort of deploy this to internally test their DRAM devices. And the hope is that, this leads to better DRAM moving forward. They get these samples from the companies, right? And then hopefully they would then run this, and then if they find bit flips, they can report to them. And then the hope is that, over time, the situation gets better. Good. So I hope that this statement that I had from before is no longer very provocative. And so DRAM is now more broken than 10 years ago. So I'm going to now switch gears and quickly talk about some of the mitigations that we have been doing. And then if there is time, I would also be happy to talk about, some of the sort of like things that are happening in industry, right? But maybe only if there is time. Okay. So how can we construct a secure mitigation? So this is some of the observation that we made, right? So that TRR is happening after a constant number of refresh commands. So every time you have a refresh, right, some of these refreshes would do TRR, right? And then this TRR would refresh a certain number of the victims. So every refresh that you would get, you would select a number of victims that you think might be getting bit flips, and you would essentially refresh them. Now let's assume an ideal implementation of TRR. So perfect frequent item count, right? Where every row has a counter, and you're precisely counting how many activations are going to which rows. The question that then we asked was, is there still an attack possible, even if you would have even if you would have the ideal implementation of the mitigation? So the observation that we made is that unfortunately there is still an attack possible, right? Because some of the rows could fly under the radar of the mitigation, even if you have precise item count. So let me show you how this would work. So imagine that you have an attack, right, where you have these 3 rows, right, and then a refresh command would come. And now this refresh, let's say you have, precise counters, right, and it would see that, okay, row B and C are activated more, right? So, and then these refresh commands would then TRR the victims of row C, okay? Because this is the one that is activated the most. And then what the attacker could do is that it doesn't care about C anymore, would instead hammer row A and B, right? And then a refresh comes that would do TRR again. The counters are 6 and 7, right? For this at this point in time, right? If you count the number of activations. And now TRR would say, okay, I'm gonna now pick row B, right? Because row B is the one that is being attacked the most. But as you can see, I've managed to push row A forward, right? By sacrificing some of the other rows along the way, right? So which would mean that even if you have a perfect counter, you could still, maybe have one of these rows. You could have some shield rows, some decoys, and protect this row, right? So that the mitigation would take these rows while this one row essentially increases its count, right? So the question is that how can the attacker maximize the number of accesses to the victim? And this is something that, this also took us like 1 or 2 years of formalization and thinking. So I'd never done formal work before in my life, and my respect for the people who do it only increased after doing it, because I realized that's actually quite hard. So, we formalized the operation of a DRAM device. We formalized how the TRR mitigation worked, and then we tried to find the optimal attack within this formalized setting, right? And then we found essentially there are a number of questions that you need to answer. So if you want the attack to work, how many of these decoys you need to have to essentially fool the TRR mitigation, right? What should your access pattern look like? And how long should the attack essentially run for? Once you answer this question, you get, so this is done by Michele, my PhD student. So he found out this attack that he called fainting, right? Which is the optimal attack against an ideal version of TRR. And then so the main idea is that, so you want to minimize the number of activation that you waste on your decoys. So that's sort of like the main idea behind the proofs. And once you minimize that, it would mean that all the other activation you could essentially use to increase the count of your attacking victim. Yeah, so and then, so the idea would be that now that we have fainting, and this is sort of like an optimal attack, it provides us with bounds, right? So if so a mitigation can withstand fainting, right, then we know that this mitigation is secure, right? And this is exactly what we did. So we built a mitigation based on misregress summaries, which are essentially counter-optimal. We try to tune the number of counters of misregress based on fainting, right? So originally we assumed so an infinite number of counters. And then misregress summaries would give you a lower number of counters that you would need to catch as many aggressors as you would need, depending on the vulnerability of your device. And then we came up with a new, because this still is a very low Rowhammer threshold, but it requires you to have a lot of counters, right? So this is not maybe something that vendors would like to do. They don't want to store too many counters. So because these counters, you know, you need to essentially implement them. They take a space, they take energy, so it increases the cost of the device, right? So, and you probably don't want to do that. So instead, we came up with a new version of fainting, which we called fainting ghost, right? And then the idea of the fainting ghost is that we could trade some of these counters, so we could reduce the number of counters while allowing for more Rowhammer vulnerability. So essentially, it would mean that, you know, the attack could assume that, okay, there are not enough counters, and while there are not enough counters, the attack could abuse this to sort of make sure that it does not need to activate the decoys as much, right? So essentially, we could go to fewer counters while increasing the threshold of the Rowhammer threshold that we would be able to withstand. So which is nice, right? So which would mean that if your device, the threshold of your device is here, right? Maybe you only need these many counters. You don't need that many counters, right? Or that many counters. And we did like sort of a lot of simulations with Gen 5. We even implemented this mitigation in ASIC in 12 nanometer technology to be able to look at, okay, how much power and energy this sort of mitigation would cost. And now I'm going to show you some results, right, from this mitigation. So here is a number of counters, right, and here is the supported Rowhammer threshold that your mitigation can support, right. And here there is this parameter D, which is the distance between TRR. So if the D is 1, it would mean that every refresh command will do a TRR mitigation, right? And if it is 15, it would mean that every 15 refresh command it would do a TRR mitigation. So here you can see, of course, if you only do TRR very rarely, you can only protect a device that has a threshold of 30K or so. So, and we have also like all the other possibilities in between. So here is DDR4, like worst DDR4s that we have, like is about 10K. So we are here, right? You can see that. And let's say you want to, your device can do every third refresh a TRR, right? So you will be here. So this would tell you, for you to be secure, you need to have 512 counters. If you would have less, basically you can bypass the mitigation. So there would be an attack possible that would bypass the mitigation because you don't have enough counters. So this is great, right? Because we reverse engineer how many counters mitigations have vendors have implemented, and it was always smaller than this minimum number of counters that we could calculate with this attack. Okay. And we also calculated the power overhead, so 2.4 to 4.7% of a static power to basically take care of these counters, and also the energy overhead is kind of tolerable, could go up to less than 0.5% in most scenarios. So this is something that is sort of like doable. But this is DDR4, and so I had prepared for you to ask, what about DDR5? Because nowadays you could go and buy DDR5 devices, right? I'm almost done. I just want to maybe say a few more things, if that's okay. Because you're going to ask about this, so I'm going to already say it, so you don't have to ask them. So I think for the attack, so these are, now I'm going to sort of put my neck out there a little bit. These are all personal opinions. These are research that we haven't done yet, right? So the first one is about the attacks, right? So will there be bit flips on DDR5, right? That's the question, the first question. So nobody has, there is no public report of any bit flip on DDR5 yet, but I personally think that it's just a matter of time. So it's just going to take time before people reverse engineer enough to understand how the vendors have implemented mitigations. So because it's a new technology, not everything will work the same, and this would mean that we have to reverse engineer some stuff. So this is just a matter of time, I think. Right. So what about defenses for DDR5? So in response to trespass, so we did responsible disclosure for trespass, right? And then in response to that, there was a task group, data integrity task group that was set up inside JDEC, which is the DRAM standardization body. And so since 2012, May, and from what I hear, they're still meeting every week. So there are like 50 engineers, 40, 50 engineers that meet every week and try to come up with ways to mitigate Rowhammer. And as an academic, this warms my heart that you're actually there. They actually forced them to try to fix this, right? And I hope that they end up with a mitigation that would essentially stop these attacks. So they've come up with a bunch of attempts, and of course I have opinions on those too, right? So the first one is refresh management. So this is something that is now natively deployed on DDR5. So you could actually buy devices that have this first attempt. This is called RFM. And then the idea is that whenever one of the banks receives a lot of activates, the memory controller should send these commands that are called RFM. And then the idea of these commands are to give time for the DRAM device to refresh more rows internally. So this is just a way for the memory controller to give more time for the DRAM device to do more mitigations. So, and this is like sort of like how it looks like. You have a counter, which is called the rolling activation counter. For a bank, activations come and these counters go up. Whenever there is a refresh received, this counter goes down. Yes?
Does that then mean there's another command that's injected?
Yeah, so the memory yeah, so you could know, but this timing side channel only tells you that you've been sending a lot of activates. Yes, there is a timing channel. You could see that another application has been sending a lot of activates. Yes, nice attack. You should do it. So here, whenever you have a ref, so this goes down, and then more activates goes up, right? Maybe ref brings it down again, but at some point, once you receive this counter saturates, now you cannot send activates to this bank anymore. You need to send this RFM command that brings it down. So the idea is that this way the device would have more time. Okay. So my personal opinion is that this is a step in the right direction, right? Giving more time for a device to essentially do the right thing. But what I'm a bit less sure about is that there is no guarantee that the DRAM vendors do the right thing once they receive these RFM commands. Okay, so that's sort of like the part of it that is maybe not so good. So what is doing the right thing? So in fainting, we saw in the paper that we published, we also formalized RFM inside this framework, and we sort of try to find out what would be the optimal attack if you would have RFM, right? And once you sort of do that, then you would know how you should configure how much your device would be able to withstand, how many counters you would need given RFM. Right, and also we of course evaluated this. So with RFM, that you could sort of like reduce the threshold. You can go even to 2-3K thresholds. Now we are at 10K, right? So you could even go to 2-3K if you do it correctly, right? And also there is some overhead that we measured. But the question is that will they do it correctly, right? This is doing it right, but the cost is not so little, right? So here you have you can see that once you have to go to counters of 1024, you're already talking like 0.1 millimeter area just for the mitigation, right? Okay. The second attempt was directed RFM. So this only became public like in October last year. So just only 2-3 months ago, right? And so the idea would be that the memory controller can tell DRAM, this row is being attacked. Please protect it, right? And then the idea would be that the next RFM will be hijacked and would try to fix this specific row that the memory controller has said might be attacked. So, I mean, this is still very new, right? Unclear who will implement it, right? But I have, again, an opinion. I think this is like a step in the wrong direction, right? And I think the reason is that now the CPU needs to do the right thing, right? It needs to sort of figure out what row is being attacked. The DRAM needs to do the right thing, right? Because the CPU may not always send these DRFMs. And both of these need to do it without knowing what the other one is going to do, right? And, we have an all-to-all problem, right? There are multiple DRAM vendors, there are multiple CPU vendors, right? So I think this is like a recipe for disaster. But this is not part of the standard, right? So we'll see what happens. And maybe even worse, it hinders offensive research that we usually do. Before, already reverse engineering one piece of hardware already would take us 1-2 years. Now we have to reverse engineer 2 pieces of hardware, right? Both the CPU and both the DRAM, which would mean that, now this is starting to become a little bit too difficult for one PhD student to do, right? So maybe this is actually, so what they did to fix it was to stop us from to do the offensive research, right? So maybe this is the solution that they found, right? Okay, finally, there is now something that is being discussed. It's called perfect Rowhammer tracking, or PRHT. So this is secret stuff, right? So we are not supposed to know about it, but people talk, right? So, and then the idea would be to implement TRR ideal inside the DRAM device, where every counter would get, every row would get a counter, but the counter is going to be inside DRAM, right? So which means that it's cheap because DRAM for storage is not expensive. So before all these counters that I showed you, they were, you know, supposed to be SRAM based counters. So this is going to be cheaper. And then the idea would be that TRR uses these counters to decide which rows to refresh. This is being considered for DDR6. So, you know, 4 or 5 years from now, it's going to be deployed. This is also like, you know, the development time of DRAM, right? So they decide now, 5 years from now, 6 years from now, you're going to get it. So I also think that this is a step in the right direction, but it requires a correct configuration according to fainting, right? Because fainting does exactly this analysis for these cases where you have an ideal TRR implementation. Do we trust the vendors to do the right thing? Let's hope so. But what if you could build a simpler mitigation that does not have counters, right? That would be great, right? If you don't rely on a state, because managing a state is hard, is also expensive, right? And this is something that we just published in security. I'm not going to talk about it, right? So this is going to generate a refresh command every time you send an activate to the device, right? And it does it in a relatively cheap way. And we did sort of an analysis. Rowhammer, the thresholds are dropping exponentially. So this is a log curve, right, on the X. So here you can see sort of we predicted where we will be 10 years from now in 2033, right? ProTRR will provide protection until here, right? If it's deployed today. And as I say, it takes 5 years for it to be deployed. So you can see already the problem, right? But if you would have such a mechanism, you could have a protection for the next 10 years. If I'm not going to talk about it, if you're interested, please read the paper or attend Michele's talk in security and privacy in a couple of months. Right, so this was everything that I wanted to say. Sorry, I went over time. The conclusion is that almost all production DDR4 devices have Rowhammer bit flips, but there is hope. I think we can fix it. I also think that there is opportunity for interesting research for newer devices, right? And I think advancing, so building mitigations in the open, like we did with ProTRR, is the way to go, right? So what vendors are doing is that they go and they do it in secret and they don't tell us what they did, right? And this is not the way it should be, right? But of course, you know, the way to force them is to do more reverse engineering and sort of like expose if they made mistakes so that they learn from it and things become better over time. And before I finish, you know, I just want to say, if you like this stuff, if you think the stuff is cool, we have multiple PhD postdocs positions. So please do apply if you like the stuff. And with that, I also want to give credit to the people who actually did the work. You know, I'm just a messenger. These are the folks who did the hard work. And also, you know, there were a lot of collaborators over the years. So some of this stuff that I told you was only possible because of their help. Thanks for listening.